In this video, we're going to continue to look at normal distributions. We're going to look at how we can use normal distributions to make predictions about the probabilities of events happening. As long as we know that the distribution is normal, we know the average, and we know the standard deviation. In particular, we're going to focus on this term called z-scores. And z-scores have a fairly straightforward definition. When you're talking about a z-score, that's just the number of standard deviations a value is from the mean. Again, z-score is just number of standard deviations we are from the mean. That's it. So let's use an example we've looked at before to illustrate. Here we have the GMAT scores. We know this is a normal distribution. They have an average of 540, average score of 540 for all people taking the GMAT, and a standard deviation of 100. So if we take all the values here, if we take various values, we might say for a value of 640, what's the z-score going to be? Well, we know 640 is one standard deviation away from the mean in the positive direction. So the z-score is going to be equal to 1. If we said the value of 340, a score of 340, that's two standard deviations to the left of the mean. So it's going to have a z-score of -2. Well, what about 540? What's the z-score for that going to be? It's going to be equal to 0. We are 0 standard deviations away from the mean. Now let's make it a tiny bit trickier. What if we said 690? What z-score would 690 be? Well, 640 is one standard deviation away from the mean, and 690 is like exactly in between 640 and 740, which would be 2 standard deviations away from the mean. And so we could say 690 has a z-score of 1.5. And that actually makes sense because we know the standard deviation is 100. 640 is 150 away from 540. So it's going to have a z-score of 1.5. How about a value of 420? What is the z-score for 420 going to be? Well, you know what? We can actually use an equation here. All we're trying to figure out is how many standard deviations is 420 away from the mean of 540 if the standard deviation is 100. How many standard deviations away is it? So we can use this equation. We can say 420 minus 540 divided by 100. That's going to be -120 over 100 equals -1.2. That's the number of z-score. That's the z-score for 420. That means we are -1.2 standard deviations away from the mean. And in fact, this is our equation for finding a z-score. It is z equals x, and x in this case is our value, the value that we're looking at in this, so all the way down this column here. X minus the mean divided by the standard deviation. This is a super important equation. It makes a lot of sense. It's not a particularly difficult equation, but it comes up all the time. So whenever you're dealing with normal distributions, you're pretty much always going to go to this equation. Now you might have different unknowns. You might not always be looking for the z-score, but you're going to come back to this equation and you're going to use it. So we're going to look at a lot of examples in this video on how you use this equation and what the z-score means and how it can be translated into probabilities. So why is the z-score important? Well, in a normal distribution, the z-scores are going to tell us everything we need to know about the distribution of results. Meaning, if we have a value and we figure out the value's z-score, it's going to tell us the percentile that is associated with that value. Don't worry if that doesn't make sense exactly right now. Let's take a look at the z-table. Quick introduction to the z-table. You may have seen this before, but the z-table shows the z-score on the leftmost column and the topmost row. In other words, the left column shows the ones place and the tenths place for a z-value, and the top row is going to extend that to the hundredths place. So if we wanted to look up, say, the z-score for -0.54, we'd go to -0.5 and find 0.04, and so then this value here is going to correspond to negative 0.54 based on the left column and the top row. Now what's inside? What are all these values inside the table? These show the proportion of results that are going to fall to the left of that z value, meaning that are less than that z value. In other words, down here when we looked up negative 0.54, this says, well, 0.2946. That's the proportion of results that are going to be to the left of negative 0.54 in a normal distribution. In other words, we could look at a curve, a normal curve, and negative 0.54 is going to be somewhere right around there. It's, you know, it's pretty close to the mean. That's the z value for negative 0.54. And the table has just told us that the proportion that's associated with falling to the left of negative 0.54 is, I don't remember it, 0.2946. This can also be translated to a percentile, which would make it 29.46%. So let's go back to our GMAT example, again with the average of 540 and a standard deviation of 100. What if we looked up, what if you had a score, say, of 705? What percentile would that put you into? In other words, what percentage of test takers would score worse than you? What percentage of test takers would score better than you? Well, first we have to figure out what's the z value associated with this value of 705. So we have to use our equation, z equals x, that's our value, minus the mean divided by the standard deviation. And x here is 705. Oops. Our mean is 540. And our standard deviation is 100. And that's going to lead us to a z value of 1.65, because this is going to be equal to 165 divided by 100 is 1.65. So let's look that up in our z table. So remember, this is our z value here, 1.65. Let's find it in our table. So I'm scrolling down until I find 1.6. Here it is. Now I'm going to look for 0.05. So this is the value that's associated with 1.65. This tells us the proportion of results that are going to be less than that z value. In other words, it tells us the proportion of results that are less than 705. So it tells us, I'm going to go ahead and make another graph here. $705 is out here, 540 is here, and 705 has a z value of 1.65, and our z table just told us that 95.05% of the results were to the left of a z value of 1.65. So this is going to be equal to 95.05%. That's your percentile. And the complement of that, which is going to be equal to 4.95%, is going to be equal to the results that scored better than you, better than 705 on the GMAT. So one thing I'm going to add to our equation here, this z equals x minus the average divided by the standard deviation, is z. The great thing about z is that you can translate z using the table into a proportion or a percentage. So all we have to do is go into the table, look up our z value, and translate it to a proportion. This can also be done backwards, and we're going to see some examples of that as well. So you might say, I know that 95% of my results are falling to the left. And again, I want to point out here, the values in here are all cumulative. So when you go down to a very, very small z-value, you're going to get a very small proportion. And it's going to go all the way up to just about 1. It's never actually going to reach 1 because those tails don't ever hit the horizontal axis, but it's going to get very, very close to 1. But these are all cumulative distributions. And you might say, well, I know that 95% of my results are going to fall to the left of this value. What is the z-score? And you can come in here and find that. Say, okay, it's going to be like 1.645 is really more accurate, and that would translate to 95%. 95% would be somewhere in between 1.64 and 1.65, and so you could say that's my z-score, and then use that in your equation as well. So z-scores and proportions are interchangeable. All right, let's look at another example. Let's say that we are looking at the height of American males, and their average, also shown using this symbol, is 70 inches tall. And their standard deviation is 3 inches. Now let's say let's say we've measured fairly accurately here. You are 65.8 inches tall. Where do you fall in terms of the spectrum? What percentage of the population is shorter than you? What percentage of the population is taller than you? All right, so we know we need to use our equation. We know first of all that we need to get the z-score for your height. And so let's use our equation to get the z-score. So z equals x, and that's going to be 65.8 minus the average divided by the standard deviation. So we're just going to plug in numbers here. 65.8 minus 70 is going to be negative 4.2 divided by 3. Negative 4.2 divided by 3 is going to be equal to negative 1.4. That's our z-score. Our z-score is going to be negative 1.4. So let's go ahead and open up the table now. Figure out what that translates to in terms of a percentage. So we find negative 1.4, and we don't have any hundredths place here, just negative 1.4. So we can go right to here to the column with a 0 in the hundredths place, and we find out that it's about 8.08% of the people are going to be shorter than you, and about 92% are going to be taller, 91.92. So I'm just going to round up a little bit and say 8% shorter, 92% taller. Let's go ahead and do, well, you know what, let's go back to GMAT scores. So again, I'm going to open up a new page, and we know, I don't have to remind you now, GMAT scores, the average is 540, the standard deviation is 100. So let's say what if we had a score of 400? What's that going to equate to in terms of percentiles? So again, same thing, 400 minus 540 divided by 100 equals negative 1.4. Okay, so we go into our table, and right, negative 1.4, we just looked that up. So we know that 8% below and 92% above. Now, I obviously engineered it this way. What I wanted to show you is that these are very different. These are very different setups. We have different averages, different standard deviations, a lot different. But the key is that if you know the z-score associated, if it's a normal curve, these are both normal distributions, no matter what your average and no matter what your standard deviations are, once you figure out the z-scores, you can figure out the proportion distribution. You can figure out the percentage So here we have the exact same z-score, even though all our other factors are different, we're still going to get the exact same proportion. This is why normal distributions are so powerful. This is why we use the z-score. All right, one last. Well, actually, we're going to do a couple more examples, but this is the one we're all going to do together. I'm going to read it to you. In a telephone call center, the typical agent averages 86 phone calls per day with a standard deviation of 11 calls. Management would prefer that agents make between 80 and 100 phone calls each day. That's kind of their sweet spot. They don't want to make too many phone calls because then that probably means they're just burning through them, but they don't want to make too few either. What percentage of agents are meeting management's expectations? In other words, what percentage of the agents are, hitting between 80 and 100 phone calls each day? Okay, so this is a little bit trickier. We actually are dealing with a range. We're not just dealing with a single value. But we can go ahead and work on it the exact same way. We're still going to use that same equation. So we're going to let's start with 100, the upper end of the range. Let's figure out our z-score for 100 phone calls. Well, our x is going to be equal to 100. We know the average for agents is 86 divided by 11. That's going to be equal to 1.27, I believe. That's our z-score on the upper end of the range. And on the lower end of the range, it's going to be 80 minus 86 divided by 11, same thing. And that's going to lead to a z-score of negative 0.545. All right, so now let's use our table to figure out what the proportions are that fall to the left of each of those values. 1.27, go to 1.2, 1.27 is here. That's going to be equal to 0.8980. And you know what? To figure out what I'm going to do next, I'm actually going to draw this thing. I find this is a very helpful thing to do, is to draw the curve and sort of figure out, just to envision everything. Here we are at 1.27, and negative 0.545 is going to be somewhere around here. And we know now everything to the left of 1.27 is going to be equal to 0.8980, or 89.8%, however you want to do this. So now, once we figure out what this value is in here, we're going to be able to subtract the one from the other, right? Because what we're really interested in is this range. This is the sweet spot. This is between 80 and 100 phone calls, because this is 80 right down here, and this is 100 up here. So that's what we're interested in. So we could take this red value, that's everything to the left of 1.27, and subtract out the blue value, which is going to be everything to the left of negative 0.545. So here we go. Let's find negative 5.545, negative 0.5, and then 45 is going to be sort of in between these two here. So it's going to be something like, I don't know, 0.298. I'll call it that. And so we ended up subtracting this from all of this, and we get 0.6. So about 60% of our agents are meeting our expectations. In other words, they're making between 80 and 100 phone calls. All right. Now, last example is one I'd like you to try on your own. So let's set it up. Now, this involves information that we worked through in a previous example. The average U.S. male is 70 inches tall, and the standard deviation on that is 3 inches. You run a t-shirt emporium that sells men's t-shirts, and every week you sell 800 t-shirts of various sizes. That's 800 t-shirts total But among those 800, you have a number of sizes represented. Using the sizes chart below, approximately how many shirts of each size should you stock in order to ensure that you're about exactly meeting customer demand? So knowing what you know about men's height in general, the average and the standard deviation, knowing how the size of your t-shirts translates to men's height, and knowing that you sell 800 t-shirts per month, per week, how many should you stock per week in order to ensure that you're just meeting demand? I'd like you to try this one on your own. If you are still a little bit intimidated by the ways to find z, how z translates to proportions and all that, then you can do it. We'll do it together. But if you want to give it a shot on your own, pause this and get going. All right. Let's solve this thing together. I've got all this information from the table pulled up in a spreadsheet here, and so let's start working through this. I've given you the inches associated with each of the sizes here of t-shirts. So we need to figure out how many standard deviations are each of these from the mean. And it might help to, you'll remember that the average is 70 and the standard deviation is 3. So we don't really need to do very complex calculations here. I can say this is -2 standard deviations from the mean. That's a z-score of -2. Down here, we know we start off at -2 and then it goes to -1. So that's the range for an extra small, is between -2 standard deviations from the mean to -1 standard deviations from the mean. Here we've got -1 to -0.33, I guess. And then we've got from -0.333 to +0.333. Now from +0.333 to, now we're back dealing with whole numbers, to 1, 1 to 2, and this is actually greater than 2. I should have had that up here as well. This should be everything less than 2 standard deviations. So now this is everything greater than 2 standard deviations from the mean. All right, now we've got our z-scores, and now we can use the z-table to find out our values. So I'm not going to do this for every one of them, but we'll do a few examples. So -2 standard deviations. Let's look that up in our z-table. -2.00 is equal to 0.0228. All right, now for the extra smalls, we're going to be starting at 0.0228, and we're going to go from there up to -1 standard deviation. So let's look up -1 standard deviation first. -1 standard deviation is 0.1587. So this is going to be equal to 0.1587 minus 0.0228, because we're going just from here to here, and this is the part that we're interested in on an extra small. Over here, that's the XXS's, and here, that's the extra smalls. So we've subtracted, this is 0.1587 was everything over here, and so then we just subtracted out everything to the left of -2 standard deviations, which was 0.0228. All right, you get the idea. So here we start off at -1 and we go up to -0.333. So -1 was, I'll have that open in a moment. -1 was 0.1587, and -0.333, we're only going to get to 0.33, but that's fine, is 3707. to 0.3707 minus 0.181587. So again, this is our proportion in between -1 standard deviation and -0.333 standard deviations. All right, I'm not going to put you through looking up all of these. I've written them down already, and I'm just going to copy them down. This is going to be equal to about 0.26. This is going to be equal to 21.2. Actually, this is going to be equal to the same thing as here. This is this is just a smooth breakdown, and so I'm going to be able to copy these down. Oops. Well. All right, so now I've got our proportions, and let's just do a quick sanity check. Let's make sure these add up to 1, because when you're talking about proportions, they all need to add up to 1. Well, close enough. That's just some little bit of rounding error. I'm going to live with that. And now, we're at the final point. We have to figure out how many t-shirts are associated with each of these proportions. Well, we know we're going to sell about 800. So we have to translate that into proportions. So we say 800 t-shirts times each of these proportions. And what we get, so these are the amounts that we should stock. And obviously we're going to have to do a little bit of rounding. These aren't perfect numbers, but that's okay. But these are the approximate numbers of t-shirts we should stock in each of these sizes in order to meet customer demand, knowing what we know about the average height of American males and the standard deviation of that height, as well as the number of t-shirts we sell per week. So again, I'm going to do a sanity check, just make sure all this equals 800. I know it's going to. Comes close enough. Have an extra t-shirt for leeway. All right, in the next video, we're going to talk about more z-score examples, more instances where we're dealing with normal distribution, and things are going to get a little bit more complicated. Thanks for bearing with me through this long example.